Okay, today we're going to talk about colloids and fine particles, looking specifically at Chapter 5 of Rhodes. The primary point to take away is that whenever you get to smaller and smaller particles, you have an increase in the surface area to mass ratio. And so if a surface area is simply related to dp squared, and the mass is related to the cube of that diameter, then you're going to end up with a ratio that says that 6 divided by dp, therefore, as you continue to increase the diameter, you increase the surface to volume ratio. Primarily, colloidal particles are ones that are going to be in the range of 1 nanometer up to about 10 microns. Once we get to much bigger than 10 microns, we're pretty much beyond that range. What we're considering is that for large masses, force is equal to mass times gravity, and so you have large body forces. But and that would be for big particles. For smaller particles, however, you end up with very high surface forces. Because the mass is low, the surface forces, which normally are negligible for larger bodies, become more and more important. There are all sorts of physical-chemical interactions which are going on. These are given names like the van der Waals forces, the electrostatic double layer. There are bridging interactions and steric interactions, and many others. The general idea being that for these smaller ones, the attraction is going to dominate. So while the individual forces may be attractive or repulsive, attraction tends to be the primary result of these forces, which leads to particle cohesion. So when we're talking about small particles, we have to talk about the concept of Brownian motion, which we've done before. And we remember that the Brownian motion is the idea that you have a particle, and it's going to start moving by somewhat random walks until it hits another molecule, it bounces off, and in general it's going to be bouncing around and might end up at some new location here. And what we're going to say is that the total distance that that particle has traveled, even though it traveled over a large range bouncing off of things, we're only interested in the ultimate distance that it traveled from beginning to end, and we're going to call that L. And we can calculate L with an equation that's related to everything under the square root, 2 times K, which is the Boltzmann constant, times the temperature T, times time, little t, all divided by 3 pi dp viscosity. And so what you see is that L is going to increase anytime you have increasing temperature or time. However, L will decrease anytime you have increasing diameter or viscosity, which makes sense. So the larger the particle is, the harder it is for it to move through the system, the lower the L. The more viscous the solution, the harder it is to move. The longer you have, the farther it can move, and the higher the temperature. So things up here, T and T, are going to make the distance L bigger, and as these things on the bottom get bigger, it's obviously going to make the distance L smaller. Now we need to talk about surface forces. So the two surface forces that are of particular interest are the potential energy and then the actual force, F. And they look very similar, but they are somewhat different. 0 is going to be given as the baseline, and you have plotting against the diameter of the particle. Actually, in this case, it's the distance from one particle to another particle. And so, initially, in the positive side of both of these, you have repulsion. So, it seems counterintuitive, but we're defining that things that are above 0 are repulsive, and things that are negative are attractive. On this line, the equilibrium position is going to be somewhat different depending on whether you're looking at potential energy or an actual force. So for an actual force, the equilibrium distance is simply going to be where the force is 0. So this would be diameter at equilibrium. For the equilibrium diameter of a potential energy, it's going to be where the potential energy is actually a minimum. So in this case, this would be the same d equilibrium diameter, depending on how we are going to plot these things. So the way we can read this is we usually start with some particle that's out at some infinite distance d. As that particle begins to get closer and closer to another particle, it starts to feel an attractive force and begins to get attracted to the particle until that attractive force goes to 0, in which case it's actually at equilibrium. And if you were to try to force the particle even closer to that, then you're going to end up getting a repulsive force, which is going to push it back to its new equilibrium distance. Similarly, if you were looking at the potential energy curve, potential energy is 0 out at some infinite distance. As you begin to push them closer and closer together, you end up getting lower and lower potential energy until you reach that equilibrium distance, and then that potential energy is going to change directions towards repulsive beyond that. And we're going to have many different types of forces. Particularly, we're going to have the van der Waals forces, which are mostly attractive. So van der Waals forces are always going to be attractive for particles that are the same. So you have two like particles in a solution, which is typically what you would have, and the particles are going to be attractive. They can be, van der Waals forces could be repulsive if you had two different particles in the same solution. But generally we'll consider those to be attractive forces for our uses. Van der Waals forces are actually divided up into several more specific forces. One's called Keeson forces, there's Debye force, London dispersion forces, etc. These tend to be dipole-dipole interactions, where charged particles are going to interact with each other. And they result from the electrodynamic interactions in a system. For instance, you have a positive nucleus around a particle, and it's going to form an electron cloud, and you have another one, and it's going to form an electron cloud. And if you have more negative forces on one side and more positive forces on another, then you're going to feel an attraction between the positive and negative parts of one particle and the positive and negative parts of the other. The electrical double layer, on the other hand, is mostly a repulsive force. It's only a few nanometers thick, and it can be measured by something called the zeta potential. The idea being that you have some particle that has perhaps positive surface charges on it. And what that's going to do is that's going to attract negative surface charges that are going to put a single layer across the surface. And then those charges in turn are going to be attracting a cloud of positive charges around that particle. And these charges are going to interact with each other in different ways. But what you can see is that the charges that are going in the solution are going to be a function of the pH. So you can imagine if you had more or less positive or negative ions in a solution, that you could then make a preference for whether or not there were more or less positive or negative charges on the surface. We'll discuss the concept of the zeta potential a little bit later. The final main force to talk about are absorbed polymers, which also are called bridging forces or steric forces. The bridging forces tend to be attractive, while the steric ones tend to be repulsive. The idea is that there are these polymers that can coat particles. They can be very long ones, and they can actually connect two particles to another, and those are also important in any system that has a polymer dissolved in it as well as the particles. Other forces that exist include things like static charges, depletion interactions, hydration forces, hydrophobic forces, etc.